Okay, our second talk will be online, will be remote, and it will be from Aofu for the paper entitled Denoising User-Aware Memory Network for Recommendation.
Hello.
How we can hear you perfectly. Whenever you're ready, you can start.
Yes. Let's begin. Hello everyone, my name is Haofu. Today I am going to present Denoising User-Aware Memory Network for Recommendation, which is completed by Alibaba Group and the University of Science and Technology of China. Recently, researchers subdivided the interaction data into implicit and explicit feedback to obtain users' unbiased preferences. Among them, explicit feedback is defined as precise but relatively rare feedback that can directly indicate users' positive or negative preferences, such as rating and tagging like or dislike. While implicit feedback refers to rich but noise feedback that cannot directly indicate the user's preferences, including click and unclick. There are two limitations on implicit and explicit feedback. First, the inherent noises of implicit feedback are not dealt with effectively. In general, click feedback may come from users accidentally clicking some wrong items. Unclick feedback includes items that the user may be interested in, but it was scrolled too fast to be noticed. Second, the existing methods are insufficient to be represent the long-term preference of users. Thus, sequential recommendation methods are all item-based methods, and the length of the item sequence used is often limited by the memory and the computing resources, which leads to the gap between the modded preference and the user's stable long-term preference. Our contributions are as follows. First, we introduce a lot of denoising user-aware memory network for CTR prediction tasks. Second, we design a future purification module to purify the noise of the implicit feedback. Third, we propose user memory network model and preference-aware interactive presentation module for fine-grained long-term preference modeling and cross-representation of long-term and short-term interests, respectively. Now, we present the details of DUMN network. The input of DUMN network can be divided into three parts, including the user profile, the target AD item, and the user behavior sequences. User behavior sequence is a list of items. In our work, we model 4 kinds of behavior sequences, which are click sequence C and unclick sequence U of implicit feedback, dislike sequence D, and like sequence L of explicit feedback. As for the embedding layer, we concatenate the different fields embedding output from the user profile and the target AD item from each user and E item respectively. After embedding sequences C, U, D, and L, the outputs are EC, U, ED, and EL respectively. For feature purification layer, it contains 2 components. The first component is the multi-head interaction attention component, and the figure of the process is shown at the upper right part. We use click sequence as an example to introduce the process. First, we feed the embedding layer's output EC of the user's click sequence into the multi-head self-attention network to obtain fine-grained preference representation. Then, we calculate the attention value between the target AD item and the item representation of each correlation in the sequence representation. Finally, we use the attention value to generate the click preference representation FC, which fuses with the target AD item's information. Similarly, we can get the representation of unclick, like, and dislike sequences as FU, FL, and FD by using the same process. The second component of feature purification layer is feature orthogonal mapping component. The goal of the feature orthogonal mapping component is to use the explicit feedback representation to purify the representation of implicit feedback sequence, which contains some noisy information. Specifically, we extract two groups of orthogonal mapping pairs, click, dislike, and unclick like, and their corresponding sequence representations are FCFD and FUFL respectively. Taking FCFD as an example, the orthogonal mapping process in a two-dimensional space is shown in the following figure. We project the first element FC of the sequence representation pair onto the second element FD's direction to get a noisy representation FPC. Then we can get a purified representation FOC in the orthogonal direction of the second element by subtracting FPC from FC. Similarly, we can get a purified representation FOU between FU of unclick sequence and FL of like sequence. As for user memory network layer, we improve the memory network used in neural Turing machine to get a more stable representation of long-term reference. And we use four memory networks, MC, MU, ML, and MD to save users click, unclick, like, and dislike references respectively. Each memory network contains M slots and two operations, including memory read and memory write. Taking MC as an example, for memory read operation, we input the concatenation results of FOC and user into the memory network MC. A controller generates a read key to address a memory. Then we generate a weight vector by traversing all memory slots. Finally, the weighted memory summary is calculated as output RC, which is a long-term interest representation. As for memory write operation, the generation process of the weight vector is similar to the memory read operation. Besides, the controller generates two additional keys, add vector and erase vector, to control the updates of the memory. Accordingly, we can get for representation of users' long-term preferences, RC, RU, RL, and RD. As for preference-aware interactive representation components, it is a gating machine to get the cross-representation of users' long-term and short-term interests. The process is shown in the following figure, and we use the representation of click preference as an example to get the cross-representation you see. The computing process is shown in the formula 13, where FOC is the short-term representation and RC is the long-term representation. The cross-representation you see, UL and UD corresponding to unclick, like, and dislike can also be obtained. Therefore, we can get the deep cross-representation across of the user by concatenating these four cross-representations. Finally, we feed the embedding outputs of the user E-user, the embedding outputs of the target's AD item E-item, and the deep cross-representation R-cross into a full connected layer with sigmoid function to generate the CTR prediction. In our proposed model DUMN network, we have two goals. For goal one, the predicted CTR of the target's item should be as close to the true level as possible. We achieve it by minimizing the average logistic of loss. For goal two, we need to ensure that the content written into these four memory networks can truly express the user's long-term preferences of click, unclick, like, and dislike. We propose an auxiliary loss based on triplet loss to help complete the memory write operation. The final loss function of DUMN network is expressed as the sum of these two losses. In the experiments, we evaluate the model onto real-world e-commerce datasets, namely Alibaba datasets and industrial datasets. For the compared baseline methods, we divide the baselines into the following two categories. The first one is non-sequence-based methods, which don't contain cross features between users and items. The second one is sequence-based methods, which capture users' interest evolution by their feedback. In particular, DMP and DFN are methods based on both implicit feedback and explicit feedback. We use the area under curve score as a metric. The results of the evolution on two datasets are recorded in Table 1. We can find that our proposed DUMN network outperforms all baselines on these two datasets. Additionally, among these two kinds of baselines, most sequence-based methods are better than non-sequence-based methods in most cases. For the ablation study, Table 2 shows the effects of user memory network layer. Table 3 shows the effects of neural Turing machine. Table 4 shows the effectiveness of preference-aware interactive representation components. Table 5 shows the effectiveness of the proposed triplet loss, and Table 6 shows the effects of implicit feedback. From the experiment results, we can find that each component of the DUMN network is helpful. Finally, we conclude our work as follows. First, we introduce a novel DUMN network to model users' preference in a funded way. Second, we introduce the FP layer to purify the implicit feedback of the users. Third, we introduce the UMN layer to capture the stable long-term preference of users. First, we introduce PIR module for cross-representation of long-term and short-term interests. Thank you.
Thank you. Thank you. Okay, so we have one question online that is a practical one, and Fernando is asking if the source code of your work is available online.
We plan to publish our code, but the process in our company, we should we will publish our code later. Yes. Yes.
Okay. And if there's no question from the audience, I'll take advantage and I'll ask one question. I saw that you used different types of interaction to model your memory networks, from clicks to likes, and I was wondering if you were planning to consider other sources of data or other sources of interaction to kind of enrich your model.
Yes, in our model, we use four kinds of feedback, including click, unclick, like, and dislike. And we think the click and unclick is a noise feedback, and in the memory network, it was proposed by the neural Turing machine, and we improve it in our work.
Okay, thank you. We have time for one final question, and Mark Ganaway is asking, what is unclick data more specifically?
Unclick data, it is present in the, such as a mobile phone. We can see the items in such as Amazon or Taobao, but we didn't click it. This data is unclick data in our work. We present it, but the user doesn't click it.
Okay, thank you. Okay, I invite you all to interact with the paper page on the hub to ask more questions to the authors, and to clap the speaker and thank him again. Thank you. Okay.